till now we have seen how we will evaluate the unknown loads or the unknown degrees of freedom using different methods, and after evaluating those displacements, how can you evaluate the stresses. So till now we are applying the loads externally to the structure, which are the mechanical loads. So we know how to calculate the stresses and how to evaluate the displacements when we have only the mechanical loads on the structure. So in this lecture we are going to see how the other effects, if we have temperature effects, how we are going to introduce them into the formulation. So thermal effects, let's consider Tm as the reference temperature. In most of the cases the reference temperature will be considered as the room temperature, ranging from 25 degrees centigrade to 30 degrees centigrade. Let's say the actual temperature which the member or the structure has subjected to be T. Then the net change in temperature we will consider it as T minus Tm. Let's call it as delta T, denote the T minus Tm term as delta T. So here we assume that there is a linear thermal elastic behavior. In that case the change in length delta L because of this change in temperature will be equal to L alpha delta T. This thing you might have been studied in your +1 or +2. Due to the thermal temperature change, how much change in length will be occurred in the member. So delta L will be equal to L alpha delta T. So because of the change in length we can evaluate the thermal strain, right? So delta L by L will be the thermal strain, then that will be equal to alpha delta T. Alpha is the thermal expansion coefficient of the member, for the material. So including these thermal effects we will be also having the mechanical loads on the member. So let's say the change in length due to those mechanical loads be dm, then the mechanical strain will be equal to change in length due to the mechanical loads, that is dm by length of the member L. So the total strain will be a combination of the mechanical strain and thermal strain, that is dm by L plus dt by L. So we know that from this expression dt by L will be equal to alpha delta T. This is alpha delta T part, this is the contribution from thermal part. So this is the contribution of strain from mechanical part. We know sigma is directly proportional to strain, sigma equal to E alpha E epsilon. So from there we can obtain the strain is equal to sigma by E. So this is one expression. Let it call as equation number 4. The total strain will be equal to, if we consider the member, if we consider a straight element, truss element, let's say one of the nodes is I, the other nodes is J. The total change in length because of these two effects will be Uj minus Ui, right? It will be displaced in this direction only in the axial. If we have an axial member in which is also a straight member, so the displacement of the member will be Uj minus Ui by L. This is the displacement and this is the actual length. So the total strain in terms of displacements is J minus Ui by L. So let us equate these two equations. From that we will get sigma by E plus alpha delta T equal to Uj minus I by L. So after equating these two terms, we will multiply E into A on both left hand side and right hand side. Then we will get sigma A plus Ea alpha delta T is equal to Ea by L Uj minus Ui. We know that stress into area will give us the force. This is the force which will be developed inside the axial member which we have considered due to the mechanical loading, and this is the force which is developed due to the change in the temperature. This is due to the temperature effect. We are representing it as Pm. M represents the mechanical and P is the load. The same for the temperature. T is the temperature, we are defining for the temperature as T, and Pt is the load due to the temperature change. This should be equal to Ea by L into Uj minus Ui. So this formulation we have obtained for a straight member or the straight element. So this is not a general formulation, right? We have seen previously also, if we have an member making an angle beta, what will be the stiffness matrix will look like, and this is how I think in the previous class we have discussed about the stiffness matrix. So we know how we can evaluate by displacing each degrees of freedom and obtain the final stiffness matrix of the structure. Similarly, if we have an arbitrary element with which is making an angle beta, we will find out how the formula will be generalized for that case, for an element making an angle beta with horizontal. So this is the element, this node is I, this node is J, and it is making an angle beta. These are the displacements in x and y directions. This is for jth node, this is for ith node. PI is the load in the x-axis direction due to mechanical loads. PI represents the load in x-axis direction, and EA alpha delta T is the thermal load. We have seen here, right? This is the thermal load, EA alpha delta T. So as of now it is in the axial direction of the member. This is angle beta. So once you resolve along the x-axis, it will be EA alpha delta T cos beta. This is the total force at ith node in the x-axis direction. This will be equal to EA by L. This is the force which will be generated at, sorry, this is the ith node, right? So this will be the force that will be generated at ith node when we activate each degrees of freedom. We have already represented this part in the stiffness matrix. If you refer the stiffness matrix in your notes, you can see this is the first row in our stiffness matrix. So this first row and the multiplication of degrees of freedom gives the load at ith node, or the first degrees of freedom point. So that is the force. So this total force should be equal to this force. Then it will be in the equilibrium. So similarly, if we evaluate for the other degrees of freedom and in the other directions also, the final expressions will be looking like this. We will get 4 individual equilibrium equations once we write in the matrix form. This is how it looks like: Pi, Qi, Pj and Qj. These are the loads in x and y directions for ith node and jth node, and EA alpha delta T will remain constant, and C represents cos and S represents sine. We have already denoted it in the short format, and this is the K matrix which we have evaluated previously also. So previously, when we have only mechanical loads, we used to have only this part. We haven't had this temperature part. We used to have only mechanical load part and stiffness matrix and degrees of freedom. Because of inclusion of this temperature effect delta T, now we have this additional part here. Now if you use this expression, if in the problem or in the design, when you go to some design company where they might have given you the delta T value which it is subjected to, or the temperature T which the structure has subjected to, then you need to include this additional part in the force vector also. Then you can evaluate the effective displacement of the element because of the temperature effect and the mechanical effects. So once you evaluate these displacements, for evaluating the stresses, you can go back to the same formulation. You can use the same formulation for evaluating the stresses, just the displacement vector will change. So in this way we can include the temperature effect and find the final degrees of freedom, and we can use this formulation for obtaining the stresses that will be developed in the member. So in general it won't be only a thermal effect. In some other effects might be, we can have moisture effect, in which the moisture of there will be difference in the moisture because of the temperature conditions outside and the fabricated materials moisture. So we will be having the moisture effect coming into place, or residual stresses which might be developed during fabricating the material of the element. There we will have some residual stresses. So these kind of effects can also be denoted by using by using delta t, or the change in temperature effect. We can get to know the displacement because of that effect. Let's say we have some residual stresses, because of that the member length has increased to some 0.2 mm, let's say, because of the residual stresses. If the actual length is L, if it is increased to L plus 0.2 mm, so then what we are going to do is we can equate that 0.2 equal to this L alpha delta t. That extra 0.2 term will be equated to L alpha delta t, and we can obtain the effective delta t for that particular change in residual stress. So we can use the same delta t here, and even we can include the effect due to the residual stresses also. So whatever may be the effect, you can convert it into thermal effect by using this delta t term, and you can evaluate the resulting degrees of freedom, and we can go back and evaluate the stresses, based on which we can design our member. So this completes our calculation of loads, degrees of freedom and reactions, even with if we have some other effects, including the mechanical loads, along with the mechanical loads. Now transformation of coordinates, this is the new topic. So how can we evaluate the load vector, or how can we evaluate the degrees of freedom vector, or how can we evaluate the stiffness matrix if there is a change in the reference coordinate system? To encounter that effect, we will first go through the transformation of coordinates theory, like how can we change the if there is a change in the coordinate system, what will be the formulation we need to include, so that we will see some examples where this will be useful, or where we need to use this formulation. So here you can see there are two coordinate systems. One is xy coordinate system, and the other is x bar y bar coordinate system. So the local coordinate system is denoted with xy, and the global coordinate system is denoted in x bar and y bar. So here we are considering a vector OA. O is the origin here, and OA is the vector which A has the coordinates x comma y, if we consider the local coordinate system, and A will be having the coordinates x bar and y bar if we consider the global coordinate system. So this is the vector. So how do we get the length? How do we come to know that this is x comma y, which part is x bar comma y bar? So once you drop a perpendicular from this point onto the desired reference axis, let us consider the x axis. If we drop a perpendicular from here, this length is x. From here, if I drop a perpendicular on x bar, this length is x bar. Similarly on y and y bar also, if we drop the perpendiculars, we will get to know the length. From here, if we consider this y and this x, we will get x comma y, and if we consider this coordinate system, y bar, x bar, this can be denoted as x bar comma y bar. Let's see how we can relate x in terms of x bar y bar, and y in terms of x bar y bar, or x bar in terms of x comma y, vice versa. So this is x, right? So let us resolve y bar and x bar onto x. This is theta. X bar y bar should be perpendicular, so this angle will be 90 minus theta. On x, if we resolve x bar, it will be x bar cos theta. When we resolve y bar, this is 90 minus theta, right? Y bar cos 90 minus theta will give sin theta. So x bar cos theta, y bar sin theta. Sorry, x bar cos theta, y bar sin theta. So x will be equal to x bar cos theta plus y bar sin theta. Similarly, you can do the same exercise for x bar also. x bar we need to resolve x and y coordinates, right? So this is x. Let's resolve x onto here. So this is x cos theta, and if we resolve y, this is 90, and this is also theta again. This part is okay. This part is 90. X between x and y it's 90. So y cos 90 plus theta. Y cos 90 plus theta will give minus sin theta. So x bar will be equal to x cos theta minus y sin theta. X bar will be equal to x cos theta minus y sin theta. I think I have made a mistake here, but in the matrix form you can see I have written the same way. Please correct this formulation. X is correct, but in the x bar formulation I have written something wrong, but in the matrix form it is correct only. So this is how we will be finding x bar and x bar x or y bar y in terms of the other coordinates. So if we write in the matrix form after obtaining or after resolving on each of the coordinate system, we will get x is c s minus s c. C is the cos and s is the sine terms. So this is x bar y bar. So this is the conversion from local to global coordinate system. This is the conversion matrix for global to local coordinate system, local coordinates matrix. So let's say this as A. So A will be equal to T times A bar. This the global coordinate system we are denoting it with bar, and when it is local there won't be any bar. Even in the further when we go further with the proofs and all, we will use the same methodology or same representation. Bar represents the global terms, and a simple alphabet will represent the local term. So T is the transformation matrix. So it is T is the transformation matrix, which is denoted as T. Similarly, if we have global also, we will have A bar, and this is, you can see here, the transpose of this will give this part. See, if we transpose this, then we will get C minus S S C, right? So this matrix is transpose of this matrix, so we are writing it as T transpose A. If we observe clearly with these two expressions, or if we compare these two expressions, let's multiply T inverse on both sides in this expression. T inverse A will be equal to I times A bar. So I times A bar will be A bar. So A bar will be equal to T inverse times A. Then if we compare these two expressions, we can get that T transpose will be equal to T inverse, which means T into T transpose equal to I, which represents an orthogonal matrix. So whenever you consider an transformation matrix, it will be always an orthogonal matrix. It is the property of the transformation matrix. When we have the coordinate transformation matrix, it will be always an orthogonal matrix. It has this property, T transpose will be equal to T inverse. This will be used later in our formulation part. Now we will go back to our finite element formulation, where KD equal to R is for structure and KD equal to R is for element. Even here also the small letters will represent for the element and the capital letters are for structure. So we know K is the stiffness matrix, D is degrees of freedom, and R is the resultant force vector. So let's see how the transformation we can apply here for our finite element formulations. We have seen for a general vector how the formulation will happen. Now we will see how we can include that for our finite element formulation. So here this is a vector, right? Even the displacement and the force values are also vectors. Only stiffness is the matrix, but these two are also vectors. So that is a vector transformation. So if we have a local coordinate system which contains u1 v1 u2 v2, that is represented as R, and the bar represents the global. If we have u1 bar, u2 bar, u3 bar, if we have a global coordinate system and a local coordinate system, then those two degrees of freedom can be related using t, similar to here a equal to t a bar. Similarly, r is t r bar. Similarly, the force vector, this is for the this is for force vector. Even for the degrees of freedom vector, it is the same. D is t times d bar. Now let's substitute these two equations in equation 10. Once you replace them here, there, we will get t times r bar will be equal to k times t d bar. So as we have seen here that T is an orthogonal matrix, when T into T transpose is multiplied, it will give an identity matrix. So we will make use of that property now. Let us multiply T transpose on both sides of this expression. Now we will get T transpose T into R bar is equal to T transpose KT times D bar. What is T transpose T? It is identity matrix. Identity matrix into R bar will give R bar. This is the formulation which we will be finally obtaining, R bar equal to T transpose KT into D bar. But what is R bar? R bar is global force vector, right? This is global degrees of freedom vector. So what should be this one? This part should be global stiffness matrix. So this should be global stiffness matrix. R bar should be equal to K bar times D bar. So we can write the K bar as T bar KT. So previously we have seen how the transformation matrix can be obtained for a vector. If you multiply it with T, we will get the transformation of a vector. In case of matrices, we need to pre-multiply T bar and post-multiply T for getting the stiffness matrix or any other matrix in global coordinate system using local coordinate system. So similarly, this we have derived for element, right? Even for structural matrix also, or for the whole structure also, it will be the same. The structural stiffness matrix capital K bar will be equal to T transpose the local stiffness matrix into T. This is how the transformation will happen in the matrices and the vectors. Now let's see how using transformation of coordinates formulation we can derive the global stiffness matrix for an inclined truss element. So here you can see the inclined truss element. Let's say it's making an angle beta, and these are the local coordinate systems which I have considered. This is node 1, this is node 2. For node 1, this is the displacement in x direction, that is u1. This is the displacement in y direction, v1. This is for node 2, this is the displacement in x direction, u2, and this is the displacement in y direction, v2. These are the local coordinate system for the selected or for the considered element inclined member of a truss. So now I will be considering one more coordinate system, which is the global coordinate system. Generally, we were interested to find the displacements or the forces in the global coordinate system. So we are considering the global coordinate system here. For x-axis, I have mentioned previously also, right? For if we have bar, we can consider that part as the global coordinate system. This is the symbol which we are using. So u2 bar will be the displacement in x direction for element 2, for the node 2, sorry. For node 1, u1 bar, v1 bar. For node 2, it is v2 bar in y direction. So now let's see. We have now u1, v1 is a vector, right? So previously we have seen the transformation for the vector from local to global. A is t times a bar. T is cs minus s and c. So here we have the global. So what's for the global? So for global to local, it is t transpose. So this will be t transpose from global coordinates, degrees of coordinates or degrees of freedom, from global degrees of freedom to local degrees of freedom. This is t transpose. If we consider this as t, so the t will change based on the system which we are taking. This is a vector which we have taken here. Now we have a truss element, so later we will see we will have a structure also. There the T matrix will be different, so the T matrix won't be the same, but it will have always the property of orthogonal property, that you have to remember. So these are the global degrees of freedom. By using the transformation matrix, we are converting into the local degrees of freedom. This is for node 1. Similarly for node 2, we can use the same formulation here. Now if I have to combine these two nodes degrees of freedoms, like a single degree of freedom vector u1 bar v1 bar u2 bar v2 bar, then this part will be coming here, and u1 bar and v1 bar are not related to u2 and v2, right? So we will be placing zeros in those places. So now if you compute u1 bar, it will be u1c minus s v1. These terms will become zeros, the same thing which we had here. So just the representation has been changed so that we can combine these two nodes degrees of freedoms. So this is the final degrees of freedom vector for this element. So this is the T matrix now. So for this element, this will be the T matrix. This is what I was saying. Like here we had a different T matrix. This is for a single vector. Now we had an element with 2 degrees of freedom. Now this is the T vector, or the T matrix. The transformation matrix will change based on our problem type. So this is how the global degrees of freedom will be converted to local degrees of freedom. So this is the T matrix in this case if we consider the element. Now if you remember, we have already derived the local stiffness matrix, right? So this is the local coordinate system with u2 and v2. So in this case, as we know that a truss element can have only axial displacements, so u1 and u2 are only possible, and v1 v2 contributions won't be there if we consider the local coordinate system. That's why we will be having zeros in the rows and columns for the stiffness matrix. So this is the local stiffness matrix for an inclined member in the local coordinate system. But what we are interested in is to find the stiffness in the global coordinate system. We have already seen 2 different methods, where structural stiffness method we have used by activating the degrees of freedom, and we have also used how we can compute an elemental stiffness matrix by resolving the forces and all in the previous classes. So now by using this transformation coordinate system transformation, how we are going to find it? See, so now we have the local stiffness matrix here, and we have the T matrix also finalized. So if we go back to the transformation of stiffness matrix thing, we have seen here how we have derived the stiffness matrix. This is the global stiffness matrix, this is the local stiffness matrix. So to evaluate the global stiffness matrix, we need to use this expression T transpose KT. So K is the local stiffness matrix which we already had. We have already derived the T matrix also. Now using this expression T transpose KT, if we evaluate the global stiffness matrix, we will obtain the matrix as this. This is the same matrix which we have found previously. So this is how, by using the transformation matrix, we can find the elemental stiffness matrix using the local coordinates and global coordinates. How we are going to find the stiffness matrix we have seen here. Now this is for a single element, right? Previously we have seen how the formulation can be generated. Now for a single element we have seen. Now we will see an example of for an element. We have seen for an element. So now for a structure, how we are going to find the global stiffness matrix and how this is useful, why this is useful, that also we are going to see now. So if you see the example here, this is node 1, this is node 2, and this is node 3. We have 3 truss element, and this is simply supported at node 1, and we have a roller support in node 3. But the change here is If you see the node 1 simply support condition, here if we consider the local coordinate system, what will be the local coordinate system? This is the local coordinate system x, this will be the local coordinate system y. Then if you see the global coordinate system, x bar, y bar. So for the node 1, both the local and global coordinate systems are same. So irrespective of your evaluating whether in the local or global, it is not a matter of thing for the node 1. But if we consider node 3, that is not the case. The local coordinate system is different from the global coordinate system. This is the global coordinate system for node 3, but the local coordinate system is this x comma y. So our objective is to find this k such that this is how we wanted it. We need it in the local coordinate systems. Here the local and global are same, so u bar, v bar, u2, v2. These two things, the local and global are same. But when we see the third node, we need to find u3 and v3. u3 and v3 need to be evaluated. We are considering only u3 and v3 because see here we have a roller support, right? So what we know, if we have a roller support like this, in this direction, in the perpendicular to the roller support direction, we know the displacement is 0. So we can apply the boundary condition. If we considered u3 bar and v3 bar, we don't know the boundary condition what we need to apply. If we consider u3 bar and v3 bar, that is the reason why we have to definitely consider a local coordinate system for this support, as we know the prescribed boundary condition only in this direction. So it should be u3 and v3. Similarly, the forces also, p1, q1 bar, p2 bar, q2 bar. As we have considered u3 and v3, the forces should be also here, should be local, p3 and q3. So previously we have seen if we convert from local to global, we have T transpose KT formulation, but it will be a bit different here. We will go through the procedure and we will get to know how we are going to evaluate the stiffness matrix for this example. So this is where when we have inclined supports or the skewed supports, this transformation coordinate formulation will be very helpful for us. So let's start with the degree of node number 3. So node number 3 will have u3 and v3, right? u3 and v3, this is local and this is global. So if we go back, for local to global it is cs minus and c. So that is the matrix which we are going to use here for third node. Similarly, if we consider node 2, it is same, right? We have discussed already. The local and global are same. So we are using a identity matrix here. u2 is equal to u2 bar, v2 is equal to v2 bar. Similarly, for the first node also, it is same. The local and global coordinates are same. So we are representing this vector in terms of this vector using an identity matrix. Now, in the previous exercise, we have done combining these two nodes degrees of freedom into a single degrees of freedom vector, right? We have combined this in this way. The first 2 by 2 matrix will be corresponds to u1 v1. The second 2 by 2 matrix will be corresponds to the second node. Similar thing we are going to do here also. The first 2 by 2 matrix will be corresponds to u1 v1. The second 2 by 2 matrix will be corresponds to u2 v2. This is 1 0 0 1. The third node degrees of freedom u3 v3 will be coming here. Here we will be having the other 2 by 2 matrix. This is u1 v1 relation, this is for u2 v2, this is for u3 v3. These are the local coordinate systems and these are the global coordinate systems. So if we go back again, so R is T R bar, right? So this is the T matrix. Now we have obtained the formulation in that way. This is that is for load, this is for D degrees of freedom, and this is D bar. D is T times D bar. D is T times D bar. So this is the T matrix or the transformation matrix in this problem. So here we have seen a different kind of T, here we have seen a different kind of T. Now in this example we are seeing a different kind of transformation matrix. So the transformation matrix will not be always the same. For the 2 by 2 vector it will be same. That is the only thing which we are going to consider and build our transformation matrix according to our problem. So now considering the global equation, R bar is K bar times D bar. So this is KD equal to R, where we are representing in global coordinate system. So let us multiply with T matrix on both the sides for converting it to the local coordinate system. Okay, we are trying to convert it. So T times R bar is, again we will be having one more T here, T K bar D bar. Now multiply, no multiplication, we have global D bar, right? If we go back here again, if we want to convert global to local, it will be D bar equal to T inverse. If we multiply with T inverse on both the sides, it is T inverse T equal to D bar. So D bar is equal to T inverse T. This is what we have obtained. If you remember again, T is a orthogonal vector, so T into T transpose should be equal to I. Based on that, we can replace T inverse with T transpose. So T times R bar will be equal to T K bar T transpose D. What is T times R bar? T times R bar is R. T times R bar is R. So we will replace T times R with R. So R equal to T times K bar T transpose T. This is the T matrix. Now we have R and D in, these are global. Now we have R and D in local. Now let's see what we are going to do. This is the local coordinate system, right? Local degrees of freedom and local loads, and T K bar T transpose and T K bar T transpose. Now if we go back to the problem, we know that local and global coordinate systems are same for 1 and 2 nodes. So we can replace U1 with U1 bar as it is same, the local and global. Similarly, we can replace V with V1 bar because the local and global are same for the node 1. Similarly, for the node 2, we can replace U2 V2 bar. So this can be replaced as U1 bar, V1 bar, U2 bar, V2 bar, and this will remain same. These are not same, right? So we will use same U3 and V3. This is T times K bar T transpose. Now similarly for the loads also, as the coordinate system of local and global are same for node 1 and node 2, P1 bar P1 will be equal, Q1 bar Q1 will be equal, P2 bar P2, Q2 bar Q2. Similarly, P3 and Q3 won't be the same with P3 bar and Q3 bar, so we will use the same P3 Q3. Now this is our objective, right? If you go back to the objective, if this is how the vectors are, we need to obtain the K matrix. Now we have obtained the K matrix, T K bar T transpose. K bar is like, we can, for individual element you can find the elemental stiffness matrix, and by using the combination of different elemental stiffness matrix we can obtain the global stiffness matrix. So this is known, this part is known, this part is also known. Now what is the advantage here is, as I have told you before, sorry, I have written wrong here, right? Yeah, the degrees of freedom vector should come here and the load vector should be here. Yes, please, if you are taking a note of it, please change it the otherwise. Here we should be having the load vector, and here we should be having the degrees of freedom vector. Here R equal to T K T D, right? So R is the load vector, so here we should be having the load vector, and this side we will have the degrees of freedom vector. So yeah, sorry for that. So now we can apply the degrees of freedom boundary conditions. What we have the boundary conditions as, U1 bar V1 bar is 0 and V3 is 0. Now we can apply those boundary conditions. As we have zeros here, we can do the elimination method for finding the unknown degrees of freedom, and later we can find the unknown load or the unknown reaction loads also. When we evaluate the loads, we will get Q3. We will get Q3 which is in this direction. So then we can resolve in the global directions, and we can derive the loads in the directly in the global coordinates only at point 3. This is how the transformation of coordinates will help when we have an inclined supports in the member. Whenever you see an inclined support, you need to definitely first build the required degrees of freedom vector. Then based on the degrees of freedom vector, we can choose the load vector. So then we need to formulate the T matrix, and we need to develop the relation between local degrees of freedom and the local degrees of freedom and the local loads in terms of stiffness matrix, and finally we can evaluate the loads and the degrees of freedom vectors. So please change this part. The load vector should be coming here and the displacement vector should be here. So that is the only change. Everything else is fine. So we have seen the T matrix won't be the same, and T matrix is always a orthogonal matrix which represents T into T transpose equal to I. So these are the two formulations which you will be useful for you: the vector transformation and the matrix transformation. The last topic, that is reflective symmetry. How, when we have some symmetry in the structure, how we will be simplifying the problem which will be given to us. So there are different types of symmetries which may exist in a structure. Like reflective symmetry can be there, which we also call as mirror symmetry, skew symmetry, axial symmetry, and cyclic symmetry structures. So in this syllabus we will be covering the reflective symmetry part. So the most common type of symmetry is also the reflective symmetry. So what do we mean by when we can say the structure is having reflective symmetry? So we can say the structure is having reflective symmetry when the size means the area, cross sectional area, the shape, it should be circular or whether it is a rectangular bar, or the shape matters, and the position of the loads in the whole structure should be similar. If we consider a plane for dividing the symmetry, so the position of load should be similar, the same place, and the material properties should be same, like the elastic modulus, and the boundary conditions, whether it is simply supported or roller, it should be the same. These should be on the opposite sides of the dividing plane, the plane which we are going to divide, used to divide. On the both sides of the plane, these things should be the same: size, shape, and the loading, the material properties, and the boundary conditions. All these 5 properties should be same. Even if the size is different and all other are same, then also we can't use this principle for simplifying our problem. Let us consider an example here. Here you can see there are 8 elements and 2, 3, 4, there are 5 nodes. 8 elements and 5 nodes. If we have 8 elements, what will be the degrees of freedom of the structure? We have seen in our first class, one element will have 2 degrees of freedom. So 8 elements will have 16 degrees of freedom. So if we consider a plane passing through 2, 4 and 3 nodes, if we pass a plane here, this is the model which we need to solve. Let's see how we are considering this as the plane. On the both sides we have simply supported boundary condition, right? We have a load which we can divide. Even the lengths of the members, this is root 2 L, this is root 2 L, the lengths are same, the cross section areas are same, these are circular members, so the member shape is also same, the elastic modulus is E, so the material properties is also same. So except this plane, we can't see any other plane which satisfies all these properties. So this is the plane which we need to consider. So that is the first step. See which plane is satisfying all these properties, then we can decide on the plane. Once we divide the structure using the plane, we need to see through which nodes this plane is going on. In this case, the plane is going through 2, 4 and 3 nodes. So once we divide the plane, we can divide the load. It will be P, and the other P will be on the other half of the structure. So once we divide the plane at the nodes, this is very critical. At the nodes, the displacement should be constrained in the perpendicular direction, so that it should not move in the perpendicular direction. Once we cut the structure using the plane, the perpendicular displacement should be restricted to 0. That we can obtain by using the roller support, right? When we have a roller support, we can have displacement in this direction, but the displacement in this direction will be restrained. This is the thing which we need to do once we select the plane, and after dividing the structure using the plane. We need to place the supports at the nodes through which the plane is passing, and such that the displacement in the perpendicular direction to that node point should be equal to 0. Now if you see, here we have 8 members and 16 degrees of freedom. Now we have only 5 members, so the degrees of freedom will be 10. So our problem will be simplified. Here we have just a small structure. If it is a large structure, and if we have this kind of symmetry available there, see, we can reduce almost 60% of the computation time in solving the problem for a large structure. So that is where this reflective symmetry technique will be very helpful for us. So whatever the displacements we obtain at node 1 will be equal to the displacements or the reaction forces we will obtain at node 5. This is how the reflective symmetric technique can be used, and please remember the boundary conditions, how we need to change at the nodes. So this concludes the part on plane trusses for plane trusses using finite element formulation. So this completes the module. If you have any doubts, please ask, so that I can clarify on the previous lectures also. You can ask the doubts which you have any.